next we're going to talk about the derivative. And the derivative is going to be another application of limits. Now, the derivative is going to be what we study for the next 7-8 weeks of this course. So it is very important. So let's first define it. Well, we'll first define it. Next week, we'll start looking at some algebraic properties of it. And then after that, we're going to look at some consequences of the derivative, some things we can do with the derivative. So first, let's define the derivative. So we're going to take this function, it could be any function, we're going to mark off a point at A, so there's A and there's the point on the function, and we're also going to take another point on this function, say at X. Then what we're going to do is draw a line which goes through those 2 points on the function that we marked off. Now this line is called a secant line because it hits a function at 2 points. But we have 2 points on this line, so we can find its slope. So we'll say m sub sec, so slope of the secant line. Well, the slope is what? Change in y over change in x. So the change in y would be f of x minus f of a. Change in x would then be x minus a. So the slope of the secant line we can find just from our slope equation. Change in y over the change in x, because we have 2 points on that line. And what we're going to do is fix this point A being there, and we're going to let this x value be variable. And what we're going to do is see what happens to this secant line as this x value approaches A. Because we can describe x approaching A with a limit. So what happens as x approaches A? Well, let's put x a little closer to A. So in these 3 graphs here, that curve is the same function, and we're looking at how the secant line changes. So A is still here, x is now a little closer to A, and we have the secant line. Let's move x a little closer yet to A. And you can see we have the secant line right there. Let x get much closer to A. And again, we're going to have the secant line. But we see in the limit as x approaches A, what would this secant line approach graphically? I'm going to finish this sentence, so there will be some words there if you're taking notes, and I'm going to do a diagram down here. So in the limit, as this x value approaches A, so A is like there, what does the secant line approach? Well, it approaches this line. So the secant line is going to approach that line as x approaches A. So we see the secant line this is saying letting x approach A, we see the secant line approaches. What does it approach? Well, this line is now touching this curve at 1 point, at just A. This line is tangent to this curve. So we see the secant line approaches a tangent line. I should spell tangent correctly. Approaches a tangent line. I should spell tangent correctly. G-E. So in the limit, this secant line is going to approach a tangent line. And the derivative is going to be a function, we'll formally define it in a moment, but it's going to be a function which gives us the slope of a tangent line. So in the limit, the secant line approaches the tangent line. What would the slope of this tangent line be? Well, it's m tan, m sub tangent. What is it? Well, it's the limit. What did we do? We let x approach A. Limit as x approaches A of the slope of the secant line, and I'll just write that down here. Limit as x approaches A. What's the slope of the secant line? Well, it's over there. F of x minus f of A all over x minus A. So right here, we have a way to find slopes of tangent lines. We could use this limit to find the slope of a tangent line. And we'll find use for this a couple times throughout the semester. But there is another set of notation we could use to define this same concept. So we'll keep this equation in mind for something we do. I think we'll do it next week. For right now, let's just consider this alternative notation. We're still going to call this point A, and we're still going to want to find a tangent line at A, as we did here. But instead of letting this other value be x, we're going to call it A plus lowercase h. So if we instead let that x value be A plus h, well, what would the slope of the tangent line be now? So A plus h, what does that h actually represent? Well, A, remember, is this x value. A plus h is this x value. So h is just measuring the distance from A that we're looking at. So the slope of the tangent line would then be, using this equation, I guess, the limit, is that going to fit here? Yeah, it should fit here. As A plus h approaches A, so the slope of the tangent line, we're still going to define it using slopes of secant line and then taking the limit, in this case, as A plus h goes back to A. Of what? Well, it's the change in y over the change in x. So the change in y, f of this value minus f of that value, the change in x, this value minus that value. And one reason that this other notation is useful is because this limit simplifies kind of nicely. So what happens as A plus h approaches A? Well, we're letting this point right here approach A. Well, remember, this is h, this is A. This is A plus h. So this right here, this distance between A and A plus h is h. So what we're really doing in letting A plus h approach A is letting this distance go to 0. But that distance, remember, is measured by h. So letting A plus h approach A is the same as letting this h approach 0. And this fraction simplifies a little too. The top doesn't simplify, so we'll still say f of A plus h minus f of A. But the bottom, you have A minus A there, so those go to 0, and h plus 0 is 0. So the denominator just simplifies to 0. So right here, we have two different notations we can use to arrive at the slope of a tangent line, which is what we're going to want the derivative to give us. So let's more formally define that. Definition. Let f of x be a function. The derivative of f of x, denoted f prime of x, so this is f, it's not to the 1 here. That's kind of like an apostrophe. It's kind of like a big straight apostrophe. So the derivative of f of x, denoted f prime of x, that's red f prime of x, is given by this equation. F prime of x equals the limit as h approaches 0, that's an h, of f of x plus h minus f of x over h. So right here, this is a function. We're going to take as our variable for our functions x for convenience, well, more for consistency. And this remark, remember what this equation gives us at a given x. Well, that equation gives us the slope of a tangent line at any given x by the first 4 boards in this lecture. So remark, f prime of x, the derivative, is the function, it's a new function, which gives the slope of the line tangent to a given function, f of x, at any x value. And we're going to do, throughout the semester, many computations with this. So right now, all we have to compute this right now is this definition. There will be questions on exam 1 and the final exam which say, do this computation using the definition. And when it says you have to use the definition, you have to use the definition, unless you don't want credit for it. Next week, we're going to see other ways we can do the computation, but the definition is very important because it ties this concept of the derivative, which we'll talk about for many weeks, into limits. And this function gives the slope of the line tangent to a given curve at any x value. Now, in the first 4 boards, we were talking mainly about fixing a point and finding the slope of a tangent line at a given point. Right here, we're just saying we can define a function that does that at any x value. So for the rest of this, we'll do mainly computations of this. We'll also do a couple applications of it. But let's start with this computation. Find f prime of x for this function. F of x equals x squared plus 4x. I'm going to do it up here. Well, we need f prime of x. What is it? Given by this limit. Limit h approaches 0 of, I'm going to write it on this board, f of x plus h minus f of x all over h. What does that equal? Well, it's still a limit. We haven't taken the limit yet. What is f of x plus h? Well, I'll write it here, and then so this will be like a side work thing, and then I'll erase it. F of x plus h. Well, take our given function, replace all x's with x plus h. So our given function is x squared plus 4x. So f of x plus h would replace all x's with an x plus h. So we have x plus h squared plus 4 times x plus h. So that's f of x plus h. I'll just write that like this up here. Will that fit? Yeah. X plus h squared plus 4 times x plus h. Replace all x's with an x plus h. So there's f of x plus h. So that's part of what we need. What's next? Next, minus f of x. Well, minus f of x, here's f of x. So we just have to subtract f of x. We have to subtract all of f of x. Maybe I should write limit a little closer. Equals limit h to 0 equals limit h to 0 of this. So we substituted everything we needed to, and now we have this equation. We have f of x plus h, which is here, minus f of x, minus all of f of x. Now, this is a limit, so you can try letting h equal 0, and you'll find in all of these, if you let h equal 0, you'll get a 0 over 0. You'll get that by design, because if you let h equal 0 over here, you get 0 over 0. And when that happens, we have some algebra to do. Well, what algebra can we do? Well, let's simplify everything and see if anything happens. So we still have limit h to 0. I'm going to move this slightly over because we might run out of room. So equals limit h to 0. What is x plus h squared? So using the the square formula. X plus h all squared is first thing squared plus 2 times the first thing times the second thing plus second thing squared. X squared, 2xh, h squared. Well, now plus 4x plus h, distribute the 4, so you get plus 4x plus 4h. And then over here, distribute that negative 1, so minus x squared minus 4x. And this is all over h. Well, what can we do with that? Well, what can we do with that? Maybe I'll get a blue marker for this. What can we do with that? Well, look at this. There's an x squared here. You can't substitute. If you try substituting here again, you'll get a 0 over 0. But there's an x squared and a negative x squared. X squared minus x squared is 0. Here's a 4x, and here's a negative 4x. 4x, negative 4x make 0. So all those things that are circled add to 0. And what are we left with? What are we left with? 2xh plus h squared plus 4h all over h. Well, what can we do with that? You let h equal 0 again. We still haven't taken the limit, so we need to write limits. What happens if you let h equal 0? Well, you get 0 plus 0 plus 0 over 0. So you still have 0 over 0. Is there any more algebra we can do here? Well, yes. I'll write it here. What other algebra can we do? Well, notice all 4 of these terms here have an h. So you can cancel an h from everything. You cancel an h from everything. Another way of saying that would be factor out an h from the top and then cancel that h with this h in the bottom. But you cancel an h from everything. You have a 2x here, an h here, a 4 here, and it's all divided by 1, so I'm not even going to write that. But now you've canceled the h's. You've canceled an h over h. That eliminated what was causing a 0 over 0 to appear. And now you can let h equal 0, or you could say that you could apply the algebraic limit laws. If you let h approach 0, let h go to 0, 2x doesn't change, h goes to 0, 4 doesn't change, so we just get 2x plus 4. Well, that's great. So we found a derivative of the, well, we found the derivative of this function. Well, what can we do with that? Well, we can do lots of things. Let's do 2 things with it. So that remark says that this function gives the slope of a tangent line to this function at a given point. So let's do example. Let's do 2 parts. A, find an equation for the line tangent to f of x equals x squared plus 4x at what? Let's do at, let's pick an odd number. X equals, how about, let's just make it a positive. I was debating whether I'd make it an a. Let's just make it a positive. Find an equation for the line tangent to this function at x equals 3. Okay. Part B. At which x values does this function, same one, have a horizontal tangent line? So find an equation for the line tangent to this curve at x equals 3. Part B, at which x values does f of x have a horizontal tangent? I don't need the word line. Have a horizontal tangent. So where should we do that? Let's do that here. Well, maybe I shouldn't erase the remark. Let's do it here. So the first one, find an equation for a tangent line. How do we find an equation for a line? Well, we need a point and we need a slope. So what is this? A. We need a point. We need a slope. Well, what does a tangent line look like? It would look like something like this. So there's our curve and there's our tangent line. This is not drawn to scale, although it's relatively close. We need an equation for this line. Well, notice the point on the curve and the point at what x? At x equals 3. Notice the point on the curve is the same as the point on the tangent line at x equals 3. So if we need a point on the line, Well, we can just choose this one on the curve when x equals 3. X equals 3. What is the point on the curve? 3 squared plus 4x. 3 squared is 9. 4 times 3 is 12. 9 plus 12 is 21. So we have a point on the curve. The point is 21. How do we find the slope of the tangent line? Well, we observe that remark. The remark says, what does the remark say? F prime gives the slope of tangent lines at any x value. So here, if we want the slope of this tangent line, which we do, we want the slope of the tangent line at x equals 3. So we need f prime of 3. Well, conveniently in the previous example, we found f prime of x. If you didn't have that given to you in the previous example, then you'd have to find f prime of x. But we had f prime of 3 in this example. F prime of x, I was debating if I should say recall f prime of x equals 2x plus 4. I'm just going to leave it down here. F prime of x is 2x plus 4. So f prime at 3 is 2 times 3 plus 4, which equals 6 plus 4, which is 10. So to find the point, we used the original function because the point on the tangent line was also on the original function. To find the slope, we used the derivative, which we found in the previous example. And now we just need to put them together. So y minus the y value equals the slope times x minus the x value. Great. Equation for a line, we need a point, we need a slope. The derivative tells us how we can find the slope. Part B, at which x values does this function have a horizontal tangent? What does a horizontal tangent look like? I'm going to draw it over, this will take 2 lines of work. I'm just going to draw it down here. What does a horizontal tangent look like? Well, it's a tangent line that's horizontal. So right there we have a horizontal tangent line. This is not this curve. It's a terrible line. Right there at the top of that hill we have a horizontal tangent. Right here we don't. That's not a horizontal tangent line. But down here we have a horizontal tangent line. Over here we have a horizontal tangent line. What happens? Well, what happens which causes the tangent line to be horizontal? Well, maybe I should phrase that differently. What is the slope of a horizontal line? Slope of a horizontal line. Change in y over change in x. What's the change in y? Well, we can pick points. Let's say this is what, 1, 5. So it's over 1, up 5. So this would be like over 4, up 5. Slope of that line? I don't know. It's 5 minus 5 over 4 minus 1. So that's 0. Slope of a horizontal line is 0. So this question is asking, find all x values at which the slope of the tangent line is 0. Find all x values at which the slope of the tangent line is 0. Find all x values at which f prime of x equals 0. Yeah, maybe I should have. In the previous example, the one where we did the computation for f prime of x, we had a long string of equalities starting up here. It said f prime of x equals limit f of x plus h, and so on. And then it got down here. Maybe I should have said after that, just make a concluding sentence, like so f prime of x. So at the end, I probably should have said that, at least for the first example, because you may have gotten lost with all those equations everywhere. In that first one, f prime of x was 2x plus 4. But here, we need x values at which the function has a horizontal tangent line. Well, we need to find where the derivative is 0. because where the derivative is 0, by this remark, the slope of the tangent line will be 0, and a horizontal line has slope 0. So I guess this will be 3 lines of work, sorry. 2x plus 4 equals 0 at what x value? Well, x equals -2. So we'll several times find equations for tangent lines. We will also consider horizontal tangent lines many times, especially in Chapter 4. But here we need a horizontal tangent line. We're looking for where the derivative is 0. Solve this, so you subtract 4, divide by 2. Let's do a couple more derivative computations. Let's do 2 more. Now let's do 3 more. So let's find f prime of x for these 3 functions. First one, x cubed minus 2. Second one, root x. Third one, 1 minus x over 2 plus x. And we're doing, the only way we know how to compute the derivative right now in this class is using the limit, using the definition. That's an h in the denominator. So for the first one, f prime x, limit as h approaches 0, f of x plus h minus f of x all over h. And what is this? Well, we have x cubed minus 2. Replace all x's with x plus h. Replace all x's with x plus h, and we get x plus h cubed minus 2. Minus f of x. Subtract all of f of x, or it won't work out. All over h. Well, that's great. So now we have some algebra to do. How do we expand a cube? Well, a couple ways. I'm leaving a space up here. A couple ways we can expand a cube. One, you can memorize a cube formula. Well, no. 1, you can just multiply everything out. 2, you can memorize a cube formula. 3, you can make a combinatorial observation. Combinatorial, C-O-M-B-I-N-A-T-O-R-I-A-L. Likely a word you've not heard before. There's a branch of math called combinatorics. And in combinatorics, you do a lot of counting and a lot of different ways of counting. Much more complicated than counting. It gets very complicated. But one thing you can do is use a combinatorial diagram, which allows us to expand a cube like that, or expand anything like that, where it's something plus something else all raised to a whole number greater than or equal to 1. And it's a diagram called Pascal's triangle, named after the mathematician. Well, not the mathematician. He was more of a, I think he was more of a scientist and a philosopher. Blaise Pascal, from what, the 1700s? Not positive of that. But Pascal's triangle, and this triangle is going to be a triangular array of numbers. And we're going to start it by putting a 1 in the top row, and then we're going to form a triangle under it by putting a 1 on each side of it in the second row. And then in the third row, maybe I shouldn't have filled it in yet. In the third row, we're again going to put 1s on both sides. And look, we're forming a triangle out here. But in the middle, to fill in this middle quantity, we're going to look at the 2 things above and diagonal from it. And we're going to add those 2 numbers together. So in this position, up there is a 1, up there is a 1. 1 plus 1 is 2. Counting. And then we'll end it again with a 1. All of these rows are going to start and end with a 1. We're just going to remember to form a triangle of numbers. And then in the next position, or in the next row, start and end with a 1. In this position, well, you look up here, you look up there, you add those numbers together. 1 plus 2 is 3. in the next position, well, you do the same thing. You know, and these positions are defined by like where there's by being underneath where there's a gap in the previous row. I mean, even these first positions, you could think of them as being 1 plus 0 if you want. Or you can think of just throwing a 1 on each side. This position, up there is a 2, up there is a 1, so we have another 3. Let's fill out a couple more rows before seeing how we're going to use this. Next row, we're going to start and end with a 1. And what do we get? Well, in this position, 1 plus 3. Next position, 3 plus 3. Next position, 3 plus 1. Last position is a 1. Now let's fill in one more row, since I don't want to write on the wall. Start and end with a 1. First position, under the 1 and the 4, 1 plus 4 is 5. Next position, between the 4 and the 6, 4 plus 6 is 10. Next position, 6 plus 4 is 10. Next position, 4 plus 1 is 5. Last position is a 1. In this triangle, you can keep forming these rows in the same way. Now this triangle, this array of numbers has many, many, many applications. One application we will use is, well, one application we will use the triangle for is expanding the cubes. Actually, that'll be the only application we use it for in this class. And how do we do this? Well, we look at the exponent. Look at the exponent. There's a 3. Look at the row where the second position is 3. So in this case, it's the 4th row. Unless you start at 0 up there, then you get it's the 3rd row. Well, but not start with 0. I meant start at row, unless you count by starting at row 0. Either way, go to the row where there's a 3 in the second position. These numbers tell you a lot. So I'm going to fill in side work down here. So side work, we're going to expand this cube. Now that row gives us the coefficient for each term. And how do we interpret that? Well, we'll see. But for now, we'll just say 1, 3, 3, 1, like that. Maybe I should have put a dot, 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 because I can keep going. Okay. So here we look at the row where the second position is 3, 1, 3, 3, 1. Those give us the coefficients. This is a positive. If that were a negative, the signs would alternate: positive, negative, positive, negative. It's a positive. It'll always be a positive since we have x plus h. And because of that, we're going to add all these together. Okay, now what do we do? Well, now we look at these terms in here. X and h. X and h. Well, and how do we use them? Well, we're going to put 3 letters on each of these terms. And we're going to follow a certain order. 3 letters on each term. The first one, x, we're going to put 3 x's here. And remember, we can write 3 x's multiplied as x cubed. Then on the next one, we're going to put 2 x's. On the next one, we're going to put 1 x. On the last one, we're going to put 0 x's. So notice the exponents on the x's go 3, 2, 1, 0. And now we're going to fill in the rest with h's, bearing in mind we need 3 letters on each term. Or you could bear in mind a different way of counting. So here, we're going to look at our next term, which is h. I'm going to write it like that, I guess. H, how many h's do we need to make a total of 3 letters? 0. How many h's do we need to make a total of 3 letters here? Well, we have 2 letters, so we need 1 more. How many here? We have 1, so we need 2 more. How many here? We have 0, so we need 3 more. So alternatively, you could have arrived at those exponents for h by noting, or by counting from 0 to 1 to 2 to 3. So how did we do this? Blob plus blob cubed. Exponent is cubed. Go to the row with a cube. Write the coefficients out. They're all positive because this is a positive, and they will always be positive in this course. So write out the coefficients, 1, 3, 3, 1, and then you look here at the x. You put 3 x's on the first, 2 x's on the second, 1 x on the third, 0 x's on the fourth. Then you look at the next letter, which is a, the next term, which is just h here. You put 0 h's here, one h here, two h's here, three h's here, and then you just simplify because, you know, when you write ones, you don't really write ones sometimes. H to the 0 is 1. 1 times x cubed is x cubed. H to the 1, you just write that as h. And similarly here, x to the 1 is just x. And on the last one, 1 times h is just, or 1 times h cubed is just h cubed. These dots were for the triangle. Maybe I shouldn't have said that while I was doing that. But right here, we see that we can expand this cube like this. So you could use the triangle, and I'm not going to say use the triangle on a test if you have to use something like it. But you could use it. Going through this and discussing it may have taken more time than just multiplying it directly, but once you get used to it, you know, you can fill these terms in much more quickly than I did by explaining them. So we're going to continue this computation, and then I'm going to talk a little bit more about Pascal's triangle. No. Yeah. No. Yeah. I don't know. Actually, Pascal's triangle might get in the way of this computation. So, I'm just going to get rid of these ones. That should get it out of the way. Okay, so I'm going to finish this computation, and then I'll do a little bit more with Pascal's triangle, and then we'll go to part B and C. This is one of the negatives of an online class. Nobody stopped me. What I wrote was incorrect. I'm glad I noticed it. That first equal sign I wrote was incorrect. Limits do not equal equations. Limits equal limits until you take the limit. Good thing I caught myself there. If I caught myself later, I'd have been very unhappy with myself. So we have that limit equals this limit. Right here, what we've written here is just the simplification for x plus h all cubed. And again, you can use the triangle, or you can you can multiply it out directly, or you can remember the cube formula, which I don't remember. Well, and then what? Well, this negative 2 is still there, and this negative will distribute through. And this is still all divided by h. So all we did here, expand the cube, distribute that negative. And now, what do we have? Well, let's look at some terms that cancel. Well, I see a negative 2 and a 2 already. Great. A negative x cubed and an x cubed. So those are going to cancel. Well, cancel meaning that those are going to add to 0. So limit as h approaches 0. What's left? Well, let's write what's left before doing anything with it. 3x squared. 3x squared h plus 3x h squared plus h cubed all over h. Well, again, if you let h equal 0, you're going to get a 0 over 0. But you'll notice that all of these terms have an h. So you can cancel an h from each thing. Or, again, alternatively, you could factor out an h on top, cancel the h's. Either way, you get to 3x squared, limit as h approaches 0, 3x squared plus 3xh plus h cubed. What was I going to say? Oh, we still haven't taken a limit yet, so you still need to write limits. But now we can let h equal 0 h squared. H cubed divided by h is h squared. So 3x squared plus 3xh plus h squared. Limit as h goes to 0. Let h equal 0, you get 3x squared plus 0 plus 0. So that's just 3x squared. So here's one limit you could use, or you could do one type of limit you could see, where you have to expand a larger equation. I don't think on a test I would ask like an x to the 5th, but I have asked x to the 4th before. So before doing, wow, talk about ineffective erasers. Before doing parts B and C, let's do a couple more examples of using Pascal's triangle. Let's do 2. Let's do 5. Now let's do 6. Let's just do x plus h because that's what we've seen. So examples illustrating Pascal's triangle. Let's just do x plus h squared, and then let's do x plus h to the 6th. Okay, x plus h squared, exponent is 2. Go to the row where the second position is a 2. Those give you the coefficients. So we have 1, we have 2, we have 1. It's positive. So we have positive signs. And now we look at our first term, which is x. We throw 2 of them on the first thing. We throw 1 of them on the second thing. We throw 0 of them on the third thing. Our other term is h. We throw 0 of them on the first thing. We throw 1 of them on the second thing. We throw 2 of them on the third thing. We simplify. And we get our square formula. How about the next one? X plus h to the 6th. Well, we need the next row of Pascal's triangle. And since I'm not going to write on the wall, it's no longer going to look that much like a triangle. But how do we form it? Well, we start with a 1, then we do 1 plus 5 is 6. 5 plus 10, 15. 10 plus 10, 20. 10 plus 5, 15. 5 plus 1 is 6, and then we end with a 1. So right there, we have the coefficients for x plus h all to the 6th. So we have a 1, we have a 6, we have a 15, we have a 20, that's probably not a space. We have a 20. I'm going to erase the rest of this because I'm not going to use it again. Where were we? 20. We have a 15. We have another 6. And we end with a 1. So we look at that row in the triangle. We write the numbers out. And actually now I'm just going to erase this too so it's out of the way. So now what do we do? Well, we follow the same pattern we did before. First term is x, but instead our exponent is 6, so we're going to put 6 x's here. 5 x's there. 4 x's. 3 x's. 2 x's. 1 x. 0 x's. Our next term is an h. So what are we going to do? Well, we're going to put 0 h's here. 1 h here. 2 h's here, 3 h's there, 4 h's there, 5 h's there, 6 h's over there, and we're just gonna, not write the ones. Well, we're gonna write that one, but not write the ones that we don't need to write. I was probably blocking that. I'm erasing because I wrote h to the 5th here instead of h to the 4th. So we get that. And you'll notice in all of these terms there are 6 letters. So again, there won't be a test question that says, show me you can use Pascal's triangle. It's just another way of doing these. In my topics in mathematics course, there might be a test question that says, use Pascal's triangle and show me, because that's a topic we cover. But that's, in calculus, that shows up just for these, so it won't be tested. Pascal's triangle. These limits with x cubed like that, with the derivative of x cubed with the definition could be tested. But if you don't want to use Pascal's triangle, you can just multiply x plus h to x plus h to x plus h and simplify. Okay, back to this question. Find f prime of x now for root x. Well, again, it equals the limit as h approaches 0, f of x plus h minus f of x all over h. Well, how do we do that here? Well, let's replace x plus h with x. What am I saying? Replace x with x plus h. And what do we get? I'm going to write it here. F of x plus h is root x plus h. Replace all x's with x plus h. Minus f of x, so minus root x, all over h. And how can we compute this limit? Well, substitution won't work. That'll give us 0 over 0. But how can we compute this limit? We've seen square roots before, and we've figured out ways to remove square roots. But here, we have 2 square roots. Can the same type of argument work? Well, maybe I should say, does the same type of argument work? Which argument is that? Well, we multiply by a convenient 1. So if you multiply the numerator by that, the square roots will go away. You multiply by that, you also have to divide by that so that we don't change the question. Well, let's see what happens if we do this. What do we get? Well, equals limit. We haven't taken the limit yet. H to 0 on top, x plus h minus x. On bottom, h times x plus h plus x with square roots. The top is because of what? The difference of squares formula. We have something minus something times something plus something, where those first somethings in each case were the same. So when you multiply them out, you get the first thing squared, which is x plus h, minus the second thing squared, which is x. Well, did that help us? I don't know. Did it? If you let h equal 0, you're still going to get a 0 over 0. But notice in the numerator, x and negative x make 0. And what happens with that? X and negative x make 0, so you're left with just h on the top. And now, look at what you have. You have an h here and an h here. So those cancel. H divided by h is 1. So you're left with limit. We still haven't taken a limit. As h approaches 0 of 1 over root x plus h plus x. Let h equal 0. What do you get? 1 over root x plus root x, which is not simplified. And right now it is simplified. So you have a root x here, they're added, so overall you have 2 root x's. So with this one, a similar simplification, well, a similar multiplication allowed for a simplification of our fraction. Similar meaning similar to limits we've already seen with square roots in them. But here we had 2 square roots to deal with. But the computation, I don't think this was a more difficult computation than the limits we did in week 2, or yeah, 2, the end of week 2. So we got that derivative 1 over 2 root x. How about the next one? Well, while I'm erasing that, why don't you start that next one and see what you get? It's kind of a pain with all the fractions, but let's see what happens. Lots of fractions to simplify. C. F prime, still a limit, h to 0, f of x plus h minus f of x all over h. What does that equal? Well, limit h approaches 0. What's f of x plus h? Maybe I should have done this without having this fraction being on that line, but I guess that's okay. F of x plus h, take f of x, replace all x's with h. So we have 1 minus x plus h over 2 plus x plus h. Minus f of x. All over h. That's a large fraction. What can we do with that? Well, I'm not going to do anything with that denominator yet. So I'm just going to write h there. Let's combine the fractions on top. To do that, we need a common denominator. What is the common denominator? Well, we'll multiply them together. And what happens to the numerator? Well, the numerator in the numerator. Well, what happens? So you need this common denominator. So we have this fraction times 2 over x over 2 over x. So we get 2 over x. We have this fraction times 2 plus x over 2 plus x. So we get what? Let's write it like this. 2 plus x times 1 minus x minus h. So notice in this step I am distributing both of these out. So we have this thing times that denominator minus this thing times that denominator to get the common denominator. So minus 1 minus x times 2 plus x plus h, and I did run out of room on that one board. And now I'm just going to make the overall fraction bar even larger. So we did nothing with the h in the bottom, but we combined the fractions on top. So we have the common denominator of this. You need to multiply the first thing by 2 plus x. You need to multiply the second thing by 2 plus x plus h. Well, now I'm going to do 2 steps of simplification at once. I'm not going to touch the overall numerator yet, but what I'm going to do is get rid of this h. How do you do that? Well, we have fraction divided by h. That's the same as fraction times 1 over h. So we have this top fraction times 1 over h, giving us a denominator of so we haven't done anything with the numerator, numerator of the numerator, I should say. So we have this top fraction times 1 over h, which is the top over this bottom times h. So right here we got rid of this overall fraction bar, but now we have to simplify the numerator. It'll look kind of weird if I put it on that fraction now. So what I'm going to do is do some side work on the numerator. So in your notes, I believe this answer should fit. If I do the side work over here, it should fit here, then equals something here. It should take about 2 or 3 more lines out, because I'm going to do the side work over here. What does this overall numerator multiply to? Well, we have a lot of distributing to do. 2 times 1 is 2. Yeah, okay, I'll do it here. 2 times 1 is 2. 2 times negative x, negative 2x. 2 times negative h, negative 2h. X times 1, x. X times negative x squared. X times negative h, negative xh. Great. We have a minus. So I'm going to write that like this. Minus what we get when we multiply this out. 1 times 2 is 2. 1 times x is x. 1 times h is h. Negative x times 2, negative 2x. Negative x times negative x, negative x squared. Negative x times negative h, negative xh. And remember, the second thing is all subtracted. So what do we have here? What cancels in this? So I'll say numerator, side, work. What happens here? What cancels? Well, let's look at what cancels. 2, negative 2, cancel. Negative 2x, positive 2x, cancel. Cancel. Positive x, negative x, cancel. What else cancels? Negative x squared, positive x squared, cancel. What else cancels? Negative xh, negative xh, negative xh, positive xh, cancel. Negative 2h minus h does not cancel, but it does make a negative 3h. So that entire numerator simplified, the entire top of the numerator simplified to just negative 3h. And now we have an h there and an h there, so we can cancel them. And I'm not going to write this next limit. I'm just, in the canceling and taking the limit, I'm just going to cancel and then take the limit because we observe that we can. H is cancel. Let h equal 0. On top you get a negative 3. Let h equal 0 on the bottom, you get 2 plus x. That's a plus sign. Times 2 plus x. Maybe I'll erase it and make it actually look like a plus sign. So on top you get a negative 3. Bottom you get 2 plus x times 2 plus x. And that's just negative 3 over 2 plus x squared. So these definitions of the derivative could get pretty complicated in their simplifications. You know, well, maybe I shouldn't say complicated. They get very unpleasant algebra could show up in many of these simplifications. So we will do a lot with the derivative in the coming weeks. Next week we will learn some other ways of computing them. But we are going to use the derivative in many, many different contexts throughout the semester. And some contexts actually make more sense with different notation for the derivative. So right here, I'm just going to discuss the different notation we're going to use for the derivative. To this point, we've just used f prime of x notation for the derivative. There are 4 other notations we can use for the derivative. So let's just talk a little about them. I'm going to have to get a new magic eraser. Good thing I have 8 of them in here. So derivative notation. For y equals f of x, the the following denote the derivative. Each of the following denotes, or I'll just say the following. Denote the derivative. The has an E at the end. So first, f prime of x, which we read f prime of x. That's the one we've seen, f prime of x. We could also, so y equals f of x, we could also just say y prime and use y with that same prime mark. We could also use dy over dx. We could use y equals f of x df over dx. We could use d by dx of f. So all three of these have the same essential way of reading them, or the same basic way of reading them. The derivative of, in this one we have dy dx, df dx, d dx of f. So the derivative of y, or f if you use f. So the derivative of y with respect to x is how you would read that one. So with respect to x just means we have a variable that we're controlling with our limit. Well, we're using the limit to control the variable. And what we mean, and well, the variable we'll be using will pretty much always be x. But keeping the variable we're taking the derivative on will be important for a few things we do. And because of that, these last three notations will be useful in certain contexts. We will probably use this third one the most. Well, I will probably use the third one the most. I find that the most useful to think about. And let me just illustrate where this the third notation comes from. So I'll say a reason for the notation dy dx. So the derivative calculus was discovered by two different mathematicians at approximately the same time in the 1600s. It was discovered by Isaac Newton. It was discovered by Gottfried Leibniz at the same time, and they did not know the other was doing essentially the same thing. But the two of them thought of what they were doing a little differently. And Newton used a notation similar to this, f prime of x. Leibniz used a notation similar to this, dy dx. So f prime of x we just defined as the limit. This notation, dy dx, has a simple, well, there's a simple reason how we can arrive at it. So I'm just going to draw a function like this. And remember what we want the derivative to do. We want the derivative to give the slope of a tangent line. And to find the slope of a tangent line, what we did was look at a secant line. But remember, the slope of a secant, or the slope of any line, could be seen directly as a change in x. Well, it can be seen directly using a change in x and a change in y. I'm going to call this point A. So right here, if we want the slope of the secant line here, well, it would be delta y over delta x. But if we want the slope of the tangent line at A, so slope of line tangent at A, so maybe I should say tangent 2f of x at A. Tangent 2f of x at A. Well, what is the slope of the line tangent to f of x at A? Well, it would be the limit which limit? Well, x is the quantity we can control. It's the variable we're taking the derivative with respect to. So we can let this delta x quantity go to 0. limit as delta x goes to 0 of the slope of the secant line. Delta y over delta x, the slope of the secant line. And this notation is simplified as a lowercase dy over lowercase dx. It's very similar to a change in y over a change in x. But to incorporate the limit and the fact that we're actually taking a limit, we're not going to use a delta. We're just going to call it a lowercase dy over dx. So all of these notations will show up throughout the semester. You might think choosing one and sticking with it would be the best idea, but there are some things we will do which I believe make much more sense with this notation. There will be some things we do which I believe make much more sense with this notation. So, the first three will definitely use more than the last two, but we will still see all of them at some point.